Hello and welcome to this lecture. We've been looking at the basic concepts of probability, sort of a quick roundup of very important ideas that play a very crucial role in the entire theory, and we've been doing it in week 1, and we're going to continue that study and look at Bayes' theorem and independence. And Bayes' theorem is always called Bayes' theorem. It's maybe technically one needs to say Bayes' theorem. It's just too much to say, so we just say Bayes' theorem and independence, at least in this class. Okay, so let's begin with a quick recap. I want to point out that many of these ideas you probably already saw in statistics 1, so this is meant to be a repetition so that quickly come up to speed. So, and this is also week 1 of the class, so that we set up the notation and everything gets set. So that's one of the main reasons why I'm sort of repeating some of the things which you probably already should know. Okay. Anyway, a quick recap. We've been talking about the probability space, which consists of the sample space, events, and the probability function. And there are 2 axioms that we start with, that we assume, and then we derived a whole bunch of properties based on that axioms, and that helped us solve problems, isn't it? So when you look at a problem, when you have a probability space, and some of the partial probabilities are available to you, some events you know about, how can you compute other things of other events, combinations, things like that. A few problems I showed you in the lecture itself. Maybe you'll see more problems in practice. So that part is that skill is very important as well. Okay, and then we saw this very, very crucial notion of conditional probability. Oftentimes the sample space is very complex. A lot of things happen one after the other, and given one event occurs, you can sort of move to this conditional probability space and do all your calculations given an occurrence of an event B, and that you can repeat. You can keep repeating, and then that ends up simplifying your calculation in such a fundamental way that conditional probability is hugely important in probability theory. Okay, and the basic idea of probability of an event given another event, right? Probability of A given B. We saw a definition for it when P of B is greater than 0, and then there is this basic relationship: probability of A intersect B is probability of B times probability of A given B, right? So that's the important relationship here. Okay, so oftentimes we found this was very useful to find probability of A intersect B, right? So you find probability of A and then B given A, or probability of B and then A given B, right? So that was easy. So the next set of lectures, some 2 or 3 lectures that maybe 4 lectures that are remaining in this topic. The first will be on something called law of total probability, which is a law which involves conditional probability and gives you again additional ammunition to attack bigger problems, more complex probability spaces, how to compute probability in such spaces. That's the law of total probability. And then Bayes' theorem. Bayes' theorem is hugely important, and that again deals with conditional probability. So how do you use conditional probability as a tool and go back and forth between very many conditional spaces and the original space, and what are the relationships between these things? Okay, so the law of total probability and Bayes' theorem together give you a complete set of tools to work with many interesting cases, and I'll also show you some interesting examples of problems that we can tackle with this idea. Okay, and finally there is this crucial notion of independence. Okay, and we'll spend quite a bit of time studying independence and why that is very crucial, and you'll see how really independence makes problem solving so much easier, right? So anything so dependence is hard to deal with in practice, and independence is so great, right? So maybe I guess that's philosophically also true. So so in probability also it's very, very true. And finally the last set of lecture for this week, the theory lectures, is on repeated trials of an experiment, independent repeated trials of an experiment, and how that gives us some very nice distributions and all. Okay, so that's recap and what's to come in this module. So let's get into the law of total probability, which builds on what we know from conditional probability to give us some additional tools. Okay, so that's law of total probability. The law itself can be stated in this very simple fashion. Let me start with the Venn diagram. I find it always easy to talk about the Venn diagram. Given the sample space S, let's say you have an event B, right? So this event B sort of partitions the sample space into 2 halves, right? There's B and there's B complement. Okay, so this picture hopefully makes sense to you. So you have sample space, there is a set B, and B complement together, they are disjoint, they make up the whole sample space, and such things are called partitions. So, B and B complement partition the sample space. So, that picture is sort of shown here. And anytime you have a partition like this, anytime you have a situation in the probability space where either this has to happen or that has to happen, right. So, that is what this means, right. So, what does this mean to say B and B complement partitions? S, in any outcome, either B should have occurred or B complement should have occurred, right. So, that is sort of like a divide and conquer already, right. So, this strategy is extremely useful in solving problems. It comes again and again and again, and in probability it shows up like this, and it shows up as the partition of B and B complement. In any situation, in any probability space that you are working with, if you ever see a situation where either this has to happen or that has to happen, you can use this law, and this law is very, very powerful. You will see how it is. Okay. So, now okay, I have this event B that I know about, but B is not the event I am primarily interested in. Maybe I am interested in an event A, right. And how does that event A look? So, now this event A is this other little oval that I have drawn there, and this A will have two parts to it. Naturally, this A will split into two parts. What are the two parts that A naturally splits into? A intersect B, the part of A that is inside B, and A intersect B complement, the part of A that is inside B complement. It's quite easy to see, right. So, you can see, if I can get my pointer here, let me show you that you have here A intersect B, isn't it? A intersect B is this part, oops, and then you have A intersect B complement, which is this part, okay. This part is A intersect B complement, is that okay? And these two are disjoint, okay. So, notice what has happened, this A and B just are any two events, it does not matter what A is, what B is, right. Anytime you have an event B, either B has to happen or B complement has to happen. There is this natural partitioning of the sample space, and anytime you have a partitioning of the sample space like this, any other event A also gets partitioned, okay. A gets partitioned into the part of A that is in B and the part of A that is in B complement, okay. So, what do we know about disjoint sets A intersect B and A intersect B complement together making up the whole set A? We have our wonderful axiom 2, right, of the probability space. So, P of A is always equal to P of A intersect B plus P of A intersect B complement. That comes from axiom 2 of the probability space. Now, we have our intersections, and once we have our intersections, we know we can go into this conditional probability idea and write down the probability of intersection using conditional probability, right. So, probability of A intersect B is probability of A given B. Notice this P of A given B is actually a probability function in the conditional probability space, okay. So, it's sort of a different space, keep that at the back of your mind, even though we keep writing PP and we keep saying the same event A in this space and that space. So, keep at the back of your mind that the space is different. So, that part is important to know, but eventually you will get comfortable with the idea and you will go between the conditional space and the original space back and forth very comfortably, okay. So, you have to get to that comfort level, only then you become good at problem solving, okay. So, probability of A intersect B one can write as probability of A given B, that is the conditional probability, times P of B, okay. And then what about A intersect B complement? Probability of A given B complement times probability of B complement, okay. So, a law like this is called the law of total probability. It is a very simple law, it looks deceptively simple and it is extremely powerful, okay. So, many calculations of events where it seems like you do not even know where to start, you always start like this. You pick some other event B which makes the conditioning very easy to calculate and you are done, okay. So, this is the law of total probability. We will see a few examples as we go along, okay. So, here is the first example. So, in the first example, I have two urns. I think we have seen this before, we saw this in the context of conditional probability, and two urns with a mixture of red color marbles and blue color marbles, and my experiment is to pick an urn at random and then pick a marble inside that chosen urn at random again. So, this is the experiment we have seen, and we saw that the conditional probabilities are easy to write down, right. So, these two conditional probabilities are easy to write down. Red given urn 1, red given urn 2, blue given urn 1, blue given urn 2 is very easy to write down, okay. Now, what the law of total probability allows you to do is to find the probability of red. What's the probability that red is drawn, red ball is drawn? So, we use the law of total probability in this direct fashion, probability of red. So, either you choose urn 1 or urn 2, right. So, this is your B and B complement, right. You either choose urn 1 or urn 2, that is what happens in this experiment. So, you condition this red on urn 1 times probability of urn 1 plus probability of red given urn 2 times probability of urn 2. That is it, as simple as that. So, you plug it in, you get your answer 6 by 13. Is that okay? It's very simple, right. So, it seems deceptively simple, but in a complex or at least in a two-step experiment of this nature, where you choose the urn first and then you choose the red or blue marble. If you want to find the probability of the color of the marble finally chosen, you always condition on the first step, right. So, you condition and then you just condition on all possibilities that can happen in the first step, and then you move to the next step, etc., etc. Okay, so you can do like this. Alright, we saw this little artificial sort of problem with the two urns and the colored marbles. Let us see a slightly different sort of probability space which maybe occurs in real life, and you want to look at a phenomenon which is more real life maybe, right. So, here is a problem. This is again from your textbook, the textbook that we have been using for this course. This is about an economic model and some computation of a probability inside that economic model. Okay, let us read it. So, you have an economic model which predicts that if interest rates rise, there is a 60% chance that unemployment will increase. But if interest rates do not rise, then there is a 30% chance that unemployment will increase. Okay, is that okay? So, once again you can see already, you can see the way the law of total probability is going to come in, the way there are two events B and B complement. Okay, so there is two situations here, either the interest rates rise or the interest rates do not rise. Right. If the interest rate rise, something happens to unemployment. If the interest rates do not rise, something else happens to so the chance of unemployment increasing changes. Okay. So, these are things that the economist gives you. Now, you have to calculate, right, given this setting in the probability space sort of roughly, right. So, notice once again these kind of problems, you do not try to think of sample space and all these, just work with events directly. Okay. What should one calculate as the probability that unemployment will increase? Okay, so let us see this. It is quite easy to solve this with the tools that we have now, the law of total probability. Probability of unemployment increase equals, so I will just call this UI, right. So, just to as a shortcut, probability of UI given interest rates rise, isn't it. So, I will say this is my event B, okay. Interest rates do not rise, this is my event B complement, isn't it. So, probability of unemployment increase given B times probability of B, okay, I think my pen was not held properly, okay, plus probability of unemployment increase given B complement times probability of B complement. Okay. So, now the question gives you the probability of unemployment increase given B is 60%. And what about probability of B itself? The economist believes that there is a 40% chance that the interest rates will rise. So, that is 0.40 plus what is the probability of unemployment increase given B complement, which is interest rates do not rise, right, and then that is 0.30 as given in the problem. What is probability of B complement? Again, you know from the properties of 0.4 is probability of B, 0.6 is probability of B complement. Okay, so after this it is just arithmetic. I have 0.24 plus 0.18, which will add up to 0.42. Okay, so there is a 42% chance overall that unemployment will increase whatever happens to the interest rate. Okay, so that is a simple calculation. So, you can see how the law of total probability is very useful, very simple. It gives you just one more easy way to keep increasing the events for which you can calculate probabilities for. Okay, in any problem setting, any probability space that you come in, you will only be able to assign probabilities to some events, right. Some of these events will be measurable, easy for you to set up a survey or something, or ask a few people, find something, and then once you assign probabilities to few events, you should always go off and calculate all the other probabilities that these things imply, right. So that kind of a setup and that kind of comfort with manipulating probabilities for events and calculating probabilities for new and new events is very, very useful. So from whatever it is that you can actually set up an experiment or actually survey and find, you should be able to extend to other events of interest. Okay, so let's get a little bit more general here. So let's say we go a little bit more general. So previously we had just one event B, and we said B and B complement partition S. Okay, so this can be generalized. How do we generalize? Maybe we have a more general partition of S. Okay, S is partitioned by B1, B2, B3 and B4. Okay, so this is just an illustration. In general, it could be more than B4, it can go B4, B5, B6, keep on going. But let's say there is a partition of S which is B1, B2, B3, B4. So what does it mean to say partition? I mean, it seems like a very independence time statement, right? Partition of the country or something. It's not so bad. A partition is very good actually. So you can do divide and conquer. So it's like one of these alternatives has to happen. Any experiment, any outcome, either B1 has to happen, or B2 has to happen, or B3 has to happen, or B4 has to happen. If you find any situation like this, then these events together will partition the sample space. Also, additionally, to say partition, these two events should be mutually exclusive. They should be disjoint. Okay, if B1 happened, B2 cannot happen, B3 cannot happen, B4 cannot happen. None of the other events can happen. So partition implies two things. Together, one of these things should happen. Okay. So the union of the whole, all the subsets is the entire sample space, yes. Then no two of them can happen together. They are mutually exclusive. They are disjoint events. So if one happened, none of the others could have happened. For instance, here if B1 happens in any outcome, if an outcome results in B1 being favorable, if an outcome is favorable to B1, it cannot be favorable to any other event that you have in the partition. Okay, so those are the conditions. So this is just generalization of B and B complement, and you can see quite readily that if you have any event A is going to naturally split into a disjoint partition once again, right. So partition once again, A intersect B1, A intersect B2, A intersect B3, A intersect B4. This is a partition, so the probabilities will add according to axiom 2, and then once you have these intersection, you can move into the conditioning subspaces, conditioning space, probability space, conditional probability spaces, and write it in terms of conditional probability. P of A given B1 times P of B1, A given B2 times P of B2, etc. Is that okay? So this is the law of total probability in its full generality. Okay. So now we are going to use the law of total probability in a slightly more general situation. Let's do that. Okay. So here's a interesting little question. It's again a toy question, maybe not too realistic in practice, but still it's an interesting toy question. There is a person who has 5 coins, and 2 of these coins are double headed. So what is double headed? It's like one of those coins in Sholay, right? So have you seen this movie Sholay? You must have seen it. There's a coin which has heads on both sides, right? So whatever you toss, you get heads. So those are 2 are double headed. One is double tailed, as in both sides are tails. Okay, somebody made a fake coin with both sides being tails. 2 others are normal. Normal meaning one side is head, other side is tails. Okay, so there are 5 of these coins. This person picks. This is a 2-step experiment, right? So what does he do? He picks a coin at random, and then he tosses it. Okay. So the probability that you have to calculate is what is the chance that he'll see a head, right? So again, you can see law of total probability sort of naturally comes into the picture, right? So P of head. Okay. So I'm going to condition on what could have happened in the first in the choice of the coin. Okay. What are the 3 things that could have possibly happened when you pick a coin? The coin should either be double headed or double tailed or normal. That's it. Those are the 3 possibilities for the coin. So you can condition on that and then your law of total probability will give you what you want. So, probability of head given, so this head I am going to call it H, given double headed, I will call it DH, okay, times probability of DH plus probability of H given dt. Now, you are following the notation, right? I do not have to say what dt is. Dt is double tailed times probability of double tailed plus probability of head given n. I do not have to say what n is, right? So, n is normal, maybe I will just write this down here for you, times probability of normal coin. Okay. So, now what is the probability? So, now let us just start writing values to this. What is the probability of H given that you picked up a double headed coin? That is going to be 1, right. So, in that conditional sample space, once you have gone into the conditional probability space, once you have gone into the double headed world, whatever you toss, you are going to get heads with probability 1. What about this guy? Probability of heads given double tailed, that is going to be 0, isn't it? So, you have gone into the coin you picked is double tailed, you toss it, you are never going to get heads. What about this world, the normal coin, you are going to get half, right. So, half, a fair coin, it is not stated here, we will assume it is fair. Okay. Now, what about this one? What is the probability that when you randomly choose from this combination, you will get a double headed coin? That is 2 by 5, right. So, 2 favorable out of 5. Again a uniform sort of distribution, this is 1 over 5, this is 2 over 5, okay, you are done, that is it. Now it is just arithmetic, right. So, you just multiply and get to the answer. Okay. So, it is 2 by 5 plus 1 by 5, I believe that is 3 by 5. Okay. So, simple calculation to show you a situation where the partition was with multiple events, more than one of them. Okay. All right. So, that is the last part of this short lecture on law of total probability. Hopefully, this was clear to you. The crucial idea is captured in this picture here. You have a partition of the sample space, you have a bunch of alternatives that have to have happened, and then you condition on them, move on to the next step, and then you can easily calculate an overall probability for any other event by breaking it down into how it intersects with each of the partitioning events. Okay. Thank you very much.